Hey everyone, and welcome to another deep dive. This time, we're tackling something pretty massive, literally, with Google's file system, GFS. You know, the system that helps Google organize, well, pretty much everything. We're diving into this fascinating research paper from way back in 2003, written by the engineers who actually built it. What's amazing is how they were already grappling with huge data challenges back then, stuff that's still relevant today.
It's true. The things they solved, like how to handle these massive data sets and that hardware, well, can fail, are even more critical now than they were back then.
Okay, so let's unpack this. Right from the start, this paper outlines these assumptions that GFS is built on. And these assumptions are not your typical file system stuff. It's like they took a look at the world of data and were like, nope, we're doing it differently.
Yeah, totally. Like how they approached hardware failures. Most systems try to avoid failures at all costs, right?
Yeah.
But they just accepted that with so much hardware, things are going to break sometimes.
So instead of panicking about every little issue, they focused on, what? Detecting those failures quickly and being able to recover automatically. Was that like a revolutionary idea back then?
Oh, yeah, absolutely. Most systems assumed failures were these rare and catastrophic events, but GFS was designed to just handle them like it was no big deal.
That's so smart. What other unusual ideas did they have?
Well, think about the size of the files they were working with. Forget kilobytes or even megabytes. GFS was built to handle files that were hundreds or even thousands of times larger. This was when most people were still trying to figure out how to burn a CD.
Wow, that's crazy. So they were already thinking about the future of data where everything's massive. How did that change how they designed the system?
It meant they had to rethink everything, from how they managed all the information about the files, the metadata, to how they made sure all that data stayed consistent, even with these giant files.
So we've got this system that can handle huge files and doesn't freak out if some hardware breaks down. But how does it all actually work? What's going on under the hood of GFS?
Well, the architecture is surprisingly elegant. It's built around a single master server, kind of like a conductor for an orchestra, keeping track of everything, but it doesn't actually deal with the data itself.
So that's where the chunk servers come in, right? Like the individual musicians, each holding a piece of the music.
Exactly. These chunk servers store the data in, get this, fixed size chunks. Each chunk is 64 megabytes.
64 megabyte. Whoa, that's a lot even now. Why so big?
It was a strategic choice. Those big chunks meant less work for the master server, kept it nice and fast, and, crucially, each chunk is copied onto multiple chunk servers, so if one server goes down...
The data is still safe.
Yeah.
Like having backup singers ready to step in if someone loses their voice.
Precisely. And talking about failures, remember how we said GFS is built to handle them? Their fault-tolerant stuff is really impressive. Both the master and the chunk servers can restart super fast, like in seconds.
So if something goes wrong, it's like a quick reboot, and they're back. No drama. That's got to be important when failures are so common, right?
Right. Absolutely. Speed is key here. Then there's that chunk replication we talked about. If a chunk server crashes, the master immediately starts copying those missing chunks to other servers. It's all about keeping the data accessible. Always.
It's like having a team ready to swap out a broken instrument in the middle of a concert. No problem.
And they even have this clever system with version numbers, like timestamps on the data, makes sure nobody uses outdated information. They even considered fancier ways to keep data safe, like using what are called erasure codes. But simple replication was, well, simpler and worked really well for them.
So simple but effective. I like it. It's awesome how they balance complexity and, well, making something that actually works. We talked about storing the data and handling crashes. But what about keeping track of it all? How do they manage the information about all these files and chunks? That seems like a massive job.
So this is where GFS does something a little different. They keep all that file system metadata, all the information about the files, in the master server's memory.
Wait, hold on. In memory. Isn't that super risky? What if the master crashes? All that information would be gone.
It does sound risky, but remember how fast that master can restart? They designed it to recover incredibly quickly, so the chances of losing data are really low. Plus, they have this detailed log of all the changes to that metadata. It's like a perfect record of every decision the conductor makes.
So even if the conductor has a momentary memory lapse, they can just check their notes and pick up where they left off.
Exactly. And to speed up recovery even more, they periodically save the master's state to disk, like taking a snapshot of the conductor's memory.
Okay, so they've got the metadata under control, but let's talk about consistency. This is where things get a little technical, but it's really important. GFS uses something called a relaxed consistency model. Now, I know relax might sound a bit careless, but stay with me here.
It's all about finding the right balance. For Google, this relaxed consistency is actually brilliant. It lets the system run much smoother, handle way more stuff without slowing down the applications that are using it.
So it's like giving the system some flexibility to do its thing. But how does it actually work?
Imagine you're making changes to a big document. With a typical system, everyone has to wait until you're completely finished saving before they can see your changes. But with GFS, they can see some of the changes as you're making them. They've got these defined and undefined regions. Some parts are guaranteed to be up to date, while others might still be changing.
It's kind of like having a live editing session where everyone can see each other's progress, even if things aren't totally in sync just yet. But how do they keep things from going completely haywire?
Well, they make sure that all the copies of the file, remember those replicas, apply the changes in the same order. It's controlled chaos. Plus, they've got this neat feature called atomic record appends, which lets multiple people add to the same file at the same time without messing anything up.
That's super important for all those Google Docs we use all the time, right? I'm starting to see why GFS is such a game changer. It's not just about the tech itself. It's about understanding what you need and making choices that really work for your situation.
Absolutely. And when it comes to performance, GFS is all about throughput over latency. They're focused on moving tons of data super fast.
So it's like choosing a big, wide highway over a small, winding road. You can get way more cars down a highway, even if each individual car takes a bit longer to reach its destination.
Perfect analogy. And that focus on moving lots of data was absolutely deliberate. It's exactly how Google uses its data.
This has been fascinating so far. We've covered how GFS stores data, how it handles failures, how it keeps track of everything, and even how it deals with keeping the data consistent. And you've explained all this complex stuff so clearly.
Well, we're just getting started. Remember, this is a system from over 20 years ago. Think about how much it's influenced the world of data since then.
That's a great point. I can't wait to hear what else you've uncovered.
But first, I think our listeners deserve a break. We'll be back soon to dive even deeper into GFS.
Okay, so we're back and ready to keep digging into GFS. Before we took a break, we were talking about how GFS is all about speed, moving lots of data quickly, kind of like a multi-lane highway designed for rush hour.
That's a great way to put it. And to make that happen, to get all that data moving, they had to come up with some really clever ways to, optimize how things move within the system.
So how does the data actually get from point A to point B in this massive system?
It's called a pipeline data flow, and it's all about making the most of the network. Imagine a bucket brigade, right? Instead of everyone crowding around while the buckets, in this case the data, are passed down the line.
So the data flows directly between the chunk servers instead of everything going through a central hub.
Exactly. Let's say you want to save data to 4 chunk servers. Instead of going to the master first and then having the master send it out, your data goes to the newest chunk server, which then passes it on to the next one, and so on.
So it's like a relay race for data.
You got it. Each chunk server gets the data, makes a copy, and passes it on.
That sounds way more efficient than having the master direct all the traffic, so to speak.
It is. And to make things even smoother, they use these persistent connections between the chunk servers. It's like having those dedicated lanes on that data highway.
Okay, so data's moving smoothly.
Yeah.
I imagine building a system like this, a distributed file system. It must have been a challenge.
Oh, absolutely. And they actually talk about some of the hurdles in the paper, some really tricky stuff.
Like what? Do they have to deal with the blue screen of death?
Not quite, but they did have some issues with, the hard drives. The drives that were storing all the data. Sometimes the drives wouldn't follow the rules, the communication protocols, and that could lead to data corruption.
Data corruption, yikes. That's like the digital equivalent of, I don't know, spilling coffee all over your important documents.
Yeah.
How do they deal with that?
Since they couldn't always trust the hardware to behave perfectly, they came up with this, really thorough checksumming scheme. It's like a built-in spell checker for the data, constantly scanning for errors.
So each piece of data gets a special code or something.
Basically, each chunk is divided into smaller blocks, and they calculate a unique checksum for each one. Every time a chunk server reads data, it checks the checksum to make sure everything matches.
If this checksum doesn't match, they know something's wrong.
Exactly. And the best part is they can automatically repair that corrupted data using those replicated copies we talked about.
So the system can basically heal itself. That's amazing.
They also had some issues with the Linux kernel, the core of the operating system. They had these performance issues with something called the fasync system call.
Okay, now that sounds a bit technical. Can you break that down for us? What does that do and why was it giving them trouble?
Well, imagine you're saving a huge file, like a giant spreadsheet. Your computer normally waits until all those changes are actually saved on the hard drive, right? But with GFS and these huge files, that could take forever.
So first thing is like hitting that save button, making sure those changes are permanent.
Yeah, exactly. But in older versions of Linux, the time it took to do that save depended on how big the file was. And with GFS, even a small change could trigger this, well, really time-consuming async operation.
Like trying to save a huge file on dial-up. Painfully slow.
Yeah. So they had to find some clever ways to work around that. They eventually switched to a newer version of Linux that had, better fsync performance.
So even Google, with all their smarts, sometimes has to deal with the limitations of, well, the tech that's available.
Oh, yeah, for sure. That's what happens when you're pushing the boundaries,
Yeah.
But they found ways to work around it, which is what matters.
Speaking of pushing boundaries, how do they keep track of what was going on in this, well, huge system? Did they have a team just staring at monitors all day?
Well, they had engineers, of course, but they relied heavily on their diagnostic tools, and monitoring systems. They knew that just building a system wasn't enough. You have to be able to see what's happening.
It's like having a dashboard with all sorts of gauges and readouts showing you the system's vital signs.
Exactly. They could track everything, like how the servers were performing, how the data was moving through the system. And if something went wrong, they had these detailed logs that could help them figure out what happened.
Like a black box recorder for the file system.
Yeah. And they didn't just use those logs for troubleshooting. They used them for performance analysis, load testing, really figuring out how to make things even better.
So it's not just about fixing problems. It's about constant learning and improvement.
Okay, I gotta ask, how did GFS actually perform in the real world? Did it live up to the hype?
Well, the paper actually gives us a glimpse into how GFS performed. They shared actual measurements from GFS clusters running at Google, doing real work, and the numbers are pretty impressive, even now.
Okay, give me the stats. How much data could it move?
Well, they found that GFS could handle read speeds of like hundreds of megabytes per second, even with hundreds of clients accessing data.
Hundreds of megabytes per second. That's like downloading an entire movie in a few seconds. It is. It really shows how well that pipeline data flow works and how much attention they paid to, optimizing the network.
Now, writing data is usually a bit slower than reading it, right? Because of that whole replication thing. Did that affect performance?
Writing is a bit more work, for sure, but they still had impressive speeds. And they also measured the load on the master server, the conductor. Even with like thousands of operations every second, the master handled it all.
Wow. So the master isn't a bottleneck. That's great.
And remember how we talked about fast recovery? Well, they tested that too. They actually simulated chunk server failures and found that GFS could recover and recreate those missing copies in just a few minutes.
That's incredible. It's like the system has a built-in safety net.
They even timed how long it took the master to restart after a crash. Usually just a few seconds.
That's faster than my laptop reboots.
Yeah.
So GFS is a high-performance system, clearly built for huge amounts of data and able to recover quickly from failures. But what was it actually doing at Google? What kind of work?
Well, the paper breaks down the workloads on two different GFS clusters. One was used for, research and development, the cutting-edge stuff. And the other was for production data processing, the everyday work that keeps Google running.
So we actually get to see how GFS was used. What kind of tasks was it performing?
They found that most of the read operations were either very small, like looking up a specific piece of information, or very large, like streaming a video. And the write operations followed a similar pattern, a mix of small updates and large writes.
And they were using those atomic record appends a lot, right? Especially in that production cluster.
Oh yeah, for sure. It's clear that GFS was designed to be really flexible, able to handle those quick lookups, the massive data transfers, all while maintaining that speed and reliability, always available.
This has been an incredible journey. We've gone from the basics of GFS all the way to seeing how it performed in the real world. I can definitely see why GFS is considered such a groundbreaking system.
And we're not done yet. Remember, this paper is from, over 2 decades ago. The world of data has changed a lot since then.
I can only imagine. Data's gotten bigger, technology's advanced, and the challenges they've definitely gotten bigger.
Right. So as you go about your day using the internet, think about all these systems running behind the scenes, storing all that data we create.
Maybe you'll be inspired to create the next big thing in data storage. Who knows? Thanks for joining us on this deep dive. We hope you found it insightful and maybe even a little bit inspiring.
Until next time, keep exploring and keep diving deep.
All right, we're back, ready to wrap up this GFS deep dive. It's been quite a journey, huh? All this talk about massive data and clever engineering. Before we paused, we were looking at how GFS performed in the real world, and those numbers, well, they were impressive. Hundreds of megabytes per second. It's kind of hard to imagine that much data flying around.
It really is, especially when you think about, they were using pretty basic hardware back then. This was 2003, remember? Not like the super-powered servers we have these days.
So it wasn't about just throwing money at the problem. It was about smart design and really getting those unique challenges of building something at this scale.
Exactly. They kind of took a step back and asked, what do we really need this system to do? What are the limits we're working with? And then they built GFS to fit those needs,
They didn't try to create a one-size-fits-all solution. They built something specifically for Google and what they needed. That's a good lesson for anyone anything complex, right? Websites, apps, even a style system. It's all about understanding what you need first.
For sure. Another big takeaway from GFS is how they embraced failure. Instead of trying to prevent every possible problem, which is basically impossible at Google scale, they designed GFS to detect and recover from those failures quickly.
They made failure just a part of the system, something to expect and deal with. It's like they built a system that could adapt and just keep going.
Exactly. And that idea goes beyond just file systems. Think about how you can make your own projects more resilient, How can you handle those bumps in the road?
That's a great point. And thinking about, GFS's influence, it's been huge for the world of data storage. So many of those ideas they came up with have made their way into other systems, other solutions.
Yeah, absolutely. Using a single master server to handle all that metadata, those big fixed-size chunks, and focusing on appending data instead of overwriting it, it's all pretty standard now.
So GFS kind of laid the foundation. It showed everyone what was possible.
Totally. It all comes back to that willingness to think differently, to challenge what everyone else was doing, and to build something that really met their specific needs.
Well, this deep dive has been honestly pretty amazing. We went from those basic building blocks of GFS all the way to seeing how it performs in the real world, how it shaped how we store data.
And keep in mind, this paper, it's just a snapshot, right? It's from 2003.
Things have changed a lot since then.
Yeah, they have. Data's exploded, technology's advanced, and those challenges, well, they've definitely gotten more complex.
So as you're using the internet, think about all those systems working in the background, storing all that data we create every day. It's incredible.
Absolutely.
Well, that's it for our deep dive into the Google file system. Hopefully you learned something new, and maybe it even sparks some ideas of your own. Thanks for listening.
Until next time.